Hi everyone, welcome back. We just finished our networking sessions. I hope you maybe got a chance to talk to some of our speakers there and met them through our Discord. Our Discord is on the home page. First up for this final block of today's talks, we have Andjela Donevic's talk called Production Eye, an intelligent system for production line monitoring. Unfortunately, Andjela couldn't be here today with us, but we have a pre-recorded session of her talk without a Q&A session at the end because unfortunately she couldn't be here. Basically, let's start the talk.
Hi, my name is Andjela, and I'm going to talk about a project that me and my team have built. It's called Production Eye, and it's an intelligent system for production line monitoring. So our client approached us with a problem. They own a company, and objects that fall during transfer cause significant operational setback for proper functioning of the whole production line. So of course we've offered a solution, and we developed an intelligent system that is able to detect anomalies during the conveyor belt transfer. Our system had to satisfy some requirements. It had to track and count both upright and falling objects. It had to track and count groups of falling objects, and of course estimate the number of the objects in a group. It had to send alert messages if any of the critical events were detected. It had to process, analyze, and save the data. And of course, it had to work in real time and have high accuracy. Here are our project phases. We've started with data collection. Then we moved on to event detection using single camera data. Here we used computer vision approach. Then we had to add some intelligence, and we used deep learning approach. Of course, we had to have our sanity check phase. Afterwards, we moved on to generalization and optimization on multiple video signals. Now we have to build application for smart production line monitoring and combine all this into our production eye intelligent system. Our data collection phase consisted of 3 steps. The first one was a selection of representative part of the production line. Then we had to set up a high resolution camera. Afterwards, we were able to move to that data acquisition. And this part of data acquisition resulted in 9 hours and 30 minutes of raw video material. About our computer vision approach, as our camera was in a fixed position, we were able to manually select the region of interest and work only with this part of the frame. It is denoted with the square in the left image. Using basic computer vision approach, we were able to remove all the unnecessary machine parts. Upright objects are detected as the circles in the frame, and then after we detected them and localized them, they were all removed, leaving us with only falling objects on the production line. Now, using advanced computer vision techniques, we are able to detect blobs that correspond to falling objects. Note that in the previous step, each blob corresponds to a unique centroid, and now given the list of centroids, we are able to develop our tracking and counting algorithm. For each centroid, we ask, is it close to an existing object? If it is close, then we add it to the existing trajectory. If it's not near an existing object, we register it as the new object. Now, if trajectory has more than n points and it has not been counted, we count it and mark it as counted. If trajectory has not been updated for k consecutive times, then we stop tracking this object. This tracking algorithm and counting algorithm has some weaknesses. For example, it is prone to registering false positive objects as new objects. We had to add some intelligence to resolve this problem. With all previous work using computer vision techniques, we were able to get labeled videos and annotated data of fallen objects and upright objects by cutting each frame into 76 by 76 patches. We were able to make this data set of course, two classes. As you can see on the right side, there are examples of fallen objects and examples of upright objects. Also, the number of instances of each class in train and test set. The model that we used is a publicly available pre-trained model, deep learning model. It's ResNet 50. It is quite big and our data is big in dimension, but our instances are small. So we used only parts, first three convolutional blocks. With this approach and training, we only trained for maybe 10 or 15 epochs, not very much. We were able to achieve high training accuracy, 99.1%, high validation accuracy, 99%, and high test accuracy. Also, both numbers for precision and recall were high and acceptable. With previously built model, we were able to implement intelligent tracking. For example, for each object that is considered to be a falling object by a basic computer vision approach, we ask our model, is it really a falling object? If our model says yes, it is, then we register it as new, and then we continue to tracking and counting. But if our model says no, it is not a falling object, then we consider it to be false positive and we carry on without registering, tracking, and counting. One of our main requirements for the system is that it has to be able to track and count groups of falling objects. Our methods for tracking falling groups of objects is quite similar to our method of tracking a single falling object. We find the group center, we track its movement and form a unique trajectory. But the main problem here is counting the number of objects in a group, because this number has to be somehow estimated. So we chose to estimate this number as the area of this blob that corresponds to a group divided by area of a single object. This estimation works fine, but it's not very precise or sometimes not very consistent. So we are working towards building a neural network model that will do smarter counting of these objects. And now let's get into sanity check part of our project. Here we had to make sure that we've met all of the basic requirements. So we did all the tracking and counting of both objects and groups of objects. And now we had to make sure that our system works in real time and has high accuracy and of course looks nice. This part of the project, it was a phase that we kept going back to and we might go back to in the future. Here is a video or demo of our part of our system. Here you can see object that has fallen and all centroids that form a unique trajectory. Here comes another one, and here are the numbers, number of upright objects and number of fallen objects. You see that objects get registered as new in this part and get deregistered as they go out of our region of interest. This one is stuck. Now you can see that many of them get stuck in the same place, and that is one of the results that we got by working on this part of the production line. Here you can see that this one didn't came fallen, but fall here in the first part of this region of interest. And one of our features that we've worked on is that we are able to determine whether the object came fallen or it has fallen somewhere in this region of interest. That would be all of our video. And now going to our results part. As I said before, we had 9 hours and 30 minutes of raw video material for the first phase or the second phase of our project. And these are the results. We detected 336 falling objects. Only 12 objects were missed by the algorithm, and we had 29 falsely detected objects. All these results are quite good because we've reached 96% of recall, or the percentage of detected falling objects out of all falling objects. And we had 92% of precision, or the percentage of correctly detected objects out of all fallen objects. And this is considered a very good improvement with what our client had before. For each time frame and of course camera position, our system is able to save object type, where object type can be upright object, fallen object, or group of object. It can save number of upright objects, number of groups, or number of fallen objects. With this data and all added information, it is able to generate reports such as this one. Here you can see the number of fallen objects for specific timestamp and whether some message was added. For example, if threshold for warning message is 10 fallen objects, here, here, and here, maybe here, all workers would get a warning message. If threshold for alert message was set for 50, if threshold for alert messages is set to 15 fallen objects, here every worker would receive an alert message. For example, this report can be generated, for example, for number of falling groups of objects or not enough upright objects, etc. So fallen object trajectories and group object trajectories are a huge part of our analytical data, and they had to be saved somehow within our database. So we decided to save them as binary images, or in the left, or heat maps shown in the right. With this data, our system is able to generate reports such as this one, where we can see that a large amount of activity happens on the right side of the production line, and our workers with this information realized that this part of the line, it was slightly tilted towards right, and they realized that by moving these machine parts, this problem was easily solved. And solving this problem resulted in decreasing the number of falling objects in this part of the production line. The fifth part, actually the fifth phase of our project, was generalization and hardware optimization. We had to generalize our algorithm so that the same solution is applicable in multiple locations and using the video signals from multiple cameras. And about the hardware part of the system consists of the following components. Of course, we had to have server, some switches or routers, of course, cameras, 5, but some can be added, and some less interesting things such as connectors, cables, etc. But of course, the main component of our hardware system is the latest generation multifunctional server with GPU support. This is the sixth part of our project, and it is still a work in progress. It is a monitoring application which will be available for all registered employees. It will consist of two parts, the user part and the administration part. Those employees who have access to the user part will have an insight into the complete history of the analytical data. They will have an option to compare the analytical data from different time intervals. They will be able to visualize them, generate reports, or export data. Those employees will have the ability to see an alarm being raised due to predefined critical event. On the other hand, employees with the administration roles will have access to the admin panel, will have the ability to define critical events or predefine the time when they will receive their daily or weekly reports. This is an example how one part of a production eye application will look like. This is the user panel, and the user will be able to select camera from 1 to the maximal number of cameras. They will see when the first session started, how many critical events have passed. They will also see the list of events with description or the list of past critical events also with description. The next part is just visualization. For example, the first camera has OK status and everything passed fine. The second camera had only warning and 2 incidents, but the third camera had 7 incidents with critical status. And that was it. Thank you for tuning in, and I hope you enjoyed this talk.